right, so last week we talked about how different beams, different structural systems, especially the beams, deform or behave under different types of loading. So today we are trying to quantify those, the bending, or how much of the deflections that they go through, how much of rotations that they go through. So we will be using a deflection, the equations for deflections for beams. Okay, so as you can see, this is a simply supported beam, supported at a pin joint over here and a roller joint on this side, and it is subjected to different types of loading. It could be the point load like this, or concentrated like P, distributed load like this, uniformly distributed, uniformly varying distributed, or whatever the type of loading that you have. So however, no matter what type of loading is applied on this beam, depending on how their magnitude is and depending on how this material is, this beam is going to deflect like this. So when we talk about beam deflection, we always look at the elastic deflection. We are not going into the plastic range, or we are not going beyond the elastic range, because we want to make sure that the structure is elastically deforming. Because when the load is applied, if it is in the elastic range, that means when you remove the load, that the beam is going back up to this original state. So if it is not the case, if it is going to be a plastic deformation, that beam is no longer coming back to its original location. Okay, so now when the beam is deflecting, so in real life you won't see this big of a, this much of a big deflection, but we are looking at an exaggerated view. So as you can see, this is called the elastic curve, right? Because this is behaving like an elastic member, and when you remove the load, it's coming back up to its original location. And the deflection is more governed by different factors. One is the applied load. The other thing is the cross-sectional properties of the beam, and also the material properties of the beam. So if you look at, this is a beam, right? So this, if you cut a section of this beam, you will see that this is a cross-sectional view of the beam. So this is the B, this is H. So this is the notation list that we have for this particular beam. So based on these factors, the load, the cross-sectional properties, the material properties, and also the boundary conditions, these deflection shapes will be different. So in order to derive the deflected shape for a given structural beam, we will be using the deflection or the bending equation for the beams. I'm sure that you have seen this equation before when you were doing structural, probably strength of materials. So M over I equals to sigma over Y. E over R is called as the bending equation for beam members. So M here is referred as the bending moment due to the external loads, right? I is called the moment of inertia about the bending axis. When you talk about a beam element like this supported by the boundary conditions, typically the beam axis will be x-axis because it's rotating or it's bending about the major axis, which is called the x-axis. And over here, this is sigma. Sigma is the bending stress, because when the beam is bending, the bending stresses will be propagated or exerted. And Y is the distance from the neutral axis to the extreme fibers. So if you remember how the beam bends, you have compression on the top, tension in the bottom. So whatever the line or the section that has no tension, no compression, it's called the neutral axis, and this y is measured from that neutral axis, right? And E here is the elastic modulus of the beam, which is a constant for a particular material. Particular material in the sense if it is concrete, it is constant for that particular material. If it is steel, it is same for the steel material, or it is if it is wood or timber, that's a constant for that particular material. And also the radius of curvature is known as R here. So in deriving the deflection curve for a beam, we will be using m over I equals to E over R relationship, and I have denoted over here. And here, this is the, I'm just trying to rearrange some of the terms here. So m equals to EI times 1 over R. So if you look at this EI, again, this is E is the material property, which is called the elastic modulus. I is the cross-sectional property, which is called the moment of inertia about the x-axis, or the moment of inertia about the bending axis. When you combine them together, it's called EI. EI is basically given as the flexural rigidity. The flexural rigidity is basically is how is it resistive to bend. For example, if you have high EI value, that means you have a high flexural rigidity. That means you have a strong member that is resisting against deflection. If you think about a material that has a lower EI value, that means it has a lower flexural rigidity. That means it is more flexible, right? And over here, 1 over R is basically known as the curvature. When the beam is bending like this, if you consider a small piece, the 1 over R is given by it is basically the curvature, how what the curvature of that elastic curve, right? So let's go to the derivation. So this might take some of the calculus interpretations and also the differential equations as well. So here, same beam, and this is called the elastic curve, right? So the elastic curve is like this because of the applied loads and also the boundary conditions. Now, what I'm going to do is I will pick very small infinitesimal piece from this elastic curve and try to look at the behavior here. So now here I'm showing you PQ is a very, very small infinitesimal piece. That means a very small piece from the elastic curve, and then we analyze the geometry of this piece. If I look at the slope at P, so the slope at P is basically given by the angle that it makes from the x-axis. So at P, the slope is theta. At Q, the slope is theta plus delta theta. The reason is that when you go from P to Q, this is a very, very small length or very small distance. Therefore, the angle or the slope is changing by delta theta. You get the difference is very, very small. Delta theta is a very, very small deformation for the angle difference. At the same time, if you see this angle over here, which is inscribed inside this triangle, this is also delta theta. That is referring to a very, very small angle. And if you consider the PQ, the location or the position, the difference is delta Y in the Y-axis, delta X in the X-axis. So from this position, right, P and Q, we will be able to derive that tan theta is equals to delta y over delta x. The reason is this is theta, right? This theta is the same theta as this theta, which is they are the same angle on the opposite side, right? And then from that, we will get this right angle triangle and then formulate for tan theta, which is delta y over delta x. Now we will apply the limits, which is coming from the calculus. Okay, so the limits are enforced to the either side of this equation when the x value is approaching to 0. The tan theta value that is equals to the x value approaches to the 0, the delta y over delta x value. By the definition of these limits, we will be able to get that tan theta equals to dy over dx. And now let's consider this as our first equation. Okay. Again, if we consider this as a segment, a circular segment, the circumference of the circular segment is called as r times the angle, right? So therefore, r delta theta equals to the PQ length, or the, let's say this is as delta S. Okay, so PQ length or delta S length is the same thing, but in different terms of different notations to make sure that we are understanding the calculus here, right? So now again, here I'm trying to rearrange now because I need delta theta over delta S term. So I have 1 over r equals to delta theta over delta S. And what I'm going to do is I'm going to assign or enforce the limits when now S is equals to or approaches to 0, 1 over r, and over here delta theta over delta S. So when we get these limits out, we will get the relationship between r and d theta and ds such that we have 1 over r equals to d theta over ds. Okay, and let's keep these two equations here. And now what I'm going to do is we will differentiate the number one, the equation number 1, with respect to s. S is, remember, the circumferential distance from P to Q. So tan theta, the derivative of tan theta in terms of theta is sec squared theta times, I'm trying to do the chain rule here, if you remember from calculus, okay, sec squared theta times theta in terms of s, because our main operator or the derivative operator is s, d theta over ds equals to, this is derivated by itself, which is d over dx, dy over dx times dx over ds. Again, I am using the chain rule to evaluate this derivation. So d theta over ds is replaced by 1 over r coming from the second equation. Okay, that is equals to d squared y over dx squared times, what is this? This is dx over ds. If we refer back to our right angle triangle, this is theta, right? So what is dx over ds? That is essentially the cosine of theta. If you were to get a cosine of theta, that would be d delta x over ds. Okay, so that is replaced by cosine of theta. And now what I'm going to do is I will get this sec squared theta over to the other side by dividing. Okay, so I will have 1 over r equals to d squared y over dx squared. Cosine theta is there, and I have 1 over sec to the power 2 theta, sec squared theta, right? And again, I know that cosine theta is 1 over sec theta. Then I will use that formulation into here. And then I will get 1 over r is equals to d squared y over dx squared times 1 over sec to the power 3 theta. Okay, right. So I have the same equation here. Okay. So I'll start from this point. So you know that from trigonometry, sec squared theta is 1 plus tan squared theta, right? So I can get sec theta as 1 plus tan squared theta, the square root of it, or the half power of this term. And then I will apply or substitute this sec to the power 3 theta in terms of this term. So if I do that, 1 over r, these are going to be the same. D squared y over dx squared will be the same. And 1 over sec to the power 3 becomes this. How is it becoming like this? Because I have sec theta. This is called the sec theta to the power 3. Sec theta is 1 plus tan squared theta to the power half. So if we raise it to the power 3, that means this is 3 over 2. So that's how this 3 over 2 is coming in. And after that, we will have this formulation. The same thing, I just multiplied by 1. So we have d squared y over dx squared divided by 1 plus, what is this tan theta? Tan theta is obtained from the equation number 1, which is dy over dx. So I substitute tan theta by dy over dx. The power is the same. I have nothing to do with it, right? And then we remind ourselves the equation that that I showed you from the bending or the bending beam equation. M is equals to the flexural rigidity times the 1 over r, which is the curvature. So here also we have the curvature, which is 1 over r. I'm trying to replace 1 over r by m over ei. So if I consider 1 over r, that is equals to m over ei. So I'm replacing it. 1 over r equals to m over ei. That is equals to d squared y over dx squared. So what happened to the bottom part here? So for small deformations or deflections, 1 plus dy over dx is approximately equals to 1. Therefore, our derivation shows us the beam deflection equation is such that this is m equals to ei d squared y over dx squared. So I used x over here because I understand that this moment is a function of x. You see this one, so this is a function of x. This is the operator, right? D squared over dx is the operator in terms of x or with respect to x. So x is basically the location that we are interested on our beam, where we find our deflection of the beam. The deflection is given by y over here. So the y is deflection, and it is a function of x. Okay, so this is basically the derivation. So we will go into an example that how we will make use of these equations. So basically, this is called the beam deflection equation. Okay, so let's move to this one. So now this is basically what we have derived so far. Mx over ei equals to the second derivative of y, which means the y is called the deflection at any point. If we consider integrating, now this is the second derivative, right? If we consider integrating one time, we can, because this is the second derivative, so if we are interested in integrating this equation one time over the length of this over the length of the beam, we will end up having integration mx over ei equals to integration d squared y over dx squared. So this is also equals to dy over dx, because the integration of d squared y over dx squared is just dy over dx. Also, this dy over dx, this is very important, okay? So dy over dx is basically a slope. If you remember from the functions, if you have a function and if you derivate it with respect to x, that will give you the slope, the behavior of the slope change. Similarly, in beams also, there's change of the slope or the rotation, because the slope is generated by the rotation of the beam by the bending. So dy over dx is called the change in the slope or the rotation. So the first integral of mx over ei is equal to the change in the slope, or it's equal to dy over dx. And again, we will, if we want to integrate it another time, that means we are integrating mx over ei 2 times. This is called the double integration. This will be equal to the double integration of d squared y over dx squared. The same thing in front of it, I am integrating in terms of 2 times. One time and the second time. And that is equals to y, which is y is the deflection of the beam at any point. So the reason why we call the double integration method, right, for finding the deflection is that we are integrating the moment over ei function 2 times. So that if we do that 2 times, we will be able to get the expression for the deflection at any point along the beam. Okay, so there are 2 things here. One is the first integral is giving you the rotation or the slope at which the beam is bending in a particular location that we are interested in. The second one is the double integration is giving you the deflection at any point that we are interested in. Okay, so again, here I'm just giving you the essence of what we have talked here. The beam rotation is equals to dy over dx. Remember, this is as a slope because it's easy that way. The slope is always related to the rotation. So the rotation of a beam is called dy over dx, and that's equals to the first integral of mx over ei dx. Mx, remember, is the bending moment variation along the beam. The beam deflection, again, it's called as y, right? Because we are integrating it another time. So we have a double integration, same thing inside here, mx over ei. But this time we are doing 2 integrations for this function. When we look at the rotation, the beam rotation, we have a sign convention such that the counterclockwise rotations are considered as positive. Therefore, clockwise rotations are known as negative rotations or negative slopes. As well as for the deflection, we have the sign convention. It is taken as upward deflections are positive. Therefore, the downward deflections are negative. Okay, so those are the 2 main equations that we will be using to determine different rotations at different locations of the beam and different deflections at different locations of the beam. Before we go into the examples, now if you look at this one, so this is an it's called it's not definite or indefinite integral. That means when we do the integration for a given function, that means we have an integration constant into into account. Okay, therefore we need to evaluate those integration constants, what they are. For that one, we will be using the boundary conditions and the continuity conditions to evaluate those integration constants, because they are the reason that we have the integration constant is that we do not have a definite region from this to this, or this limit to that limit. They are called indefinite integration or integrals. So we have two different conditions where we need to consider to evaluate these integration constants. One is the boundary conditions. The other one is the continuity conditions. So if you look at the boundary conditions, this is the same thing that we have been talking, in the past couple of weeks. So the boundary conditions is how they are restrained. So if we look at a simply supported beam restrained on a pin support at A, roller support at B. So the boundary conditions, when we assign those boundary conditions, we get to see that when the load is applied on top of AB, A is a pin support. That means it's restraining the vertical motion. Therefore, the boundary condition says that the deflection at A is equal to 0. A is not going to move. Similarly, B is also a pin support that also restrains the vertical motion. Therefore, the boundary conditions, by assigning the boundary conditions at B, we get to see that the deflection at B is equal to 0. So by assigning, for example, these boundary conditions, we know we are able to get these unknown integral constants where they are. So therefore, we will be using these boundary conditions at different locations. That is coming from the way that these supports are assigned. So for example, if we look at this beam over here, this is a cantilever beam which is fixed at A. So the boundary conditions will be at A will be the vertical displacement is 0, or vertical deflection is 0 at A. Therefore, the deflection at A is equal to 0. Since this support is restrained or fixed, the rotation is not allowed. Therefore, the rotation or the slope at A is equals to 0. Okay, so those are the two or maybe 4 boundary conditions that we can assign for these two types of beams. What about the continuity conditions? Continuity conditions is that if you consider the same simply supported beam AB, when the load is applied, this will be bending like this, so that this is called as the elastic curve. And if we are considering the deflection at C, so the C is somewhere in between the beam. So when we consider the deflection at C between AC region, so AC region is here. When we consider this AC region, the deflection at C is equal to the deflection at C when we consider CB region. Okay, so this is a continuity. So there is no discontinuity. Therefore, we say that to satisfy the continuity conditions, the deflection parameters will be something like this, which is deflection at C between AC region is equals to the deflection at C between CB region. If they are not equal, that means it's not continuous, or AC and CB members are not continuous. Okay. Similarly, the rotation also has the continuity condition. If we get the slope at C or the rotation at C, when we consider the AC member or AC region, that is exactly the same as the rotation or the slope at C when we consider the CB region. Okay, so essentially that is basically what the continuity conditions are. So those two conditions are assigned to find out the integration constants so that we will be able to get the complete equation for the elastic curve, for the deflection of the beam, and the rotation of the beam at any point.